Hello students, so in this lecture we are going to discuss about the yield process of yield taking place in crystal under shear. This is the topic. Now if you uh, look very naively, what can be said is that if you consider the crystal to be arranged in this fashion as shown in this diagram, where you have a lattice parameter in the vertical and the horizontal directions as A, and you are applying the shear force tau, and the crystal planes are two adjacent crystal planes are arranged at an angle theta with respect to each other. Now, so according to the Hooke's law, the shear force or, or the shear stress applied will be equal to this shear modulus mu into the shear strain that is taking place. Now, when this shear force is or the shear stress is high enough to cause yielding, represented by the suffix y, then the strain also gets replaced by the suffix, and assuming that this angle is 30°, we get the following relation for the shear stress to called yielding. And this can be considered to be taking place in this fashion where the atoms below or the plane of atoms, they due to the application of shear, they start moving so that there is no angle existing between them. This is the point at which the system is elastic, still elastic in nature. And after the yield point has been achieved, the process continues. So, and again, an angle of theta uh, gets built between the adjacent plane, but in a different manner. So, the lower atoms, or there is a shift of atomic planes with respect to each other when there is a plastic deformation taking place. Now, uh, there is actually the process is actually not so simple as it looks. Uh, so if we look with the details, what exactly happens during this process is, first of all, if you take a perfect crystal where there are no defects or dislocations present. Now, when these perfect crystal is subject to a shear stress, there is strain. The adjacent planes are strained in the process by to accommodate the shear stress, so that you form a dislocation. So that you can see that there is a half plane of atoms gets dislodged from its position, and it is forming a dislocation. So dislocations are formed due to shear. Now, material having such type of dislocation, when uh, it is again subject to shear, the shear is represented by this Burgess vector. So you can see, this is the half plane of atoms, which is the dislocation. It is represented by this Burgess vector B. So there is a half plane of atom here at the edge, and there is a half plane of atom at the center. So when in this condition there is further shear, the dislocation actually starts to shift. It's like a movement of a caterpillar. Yeah. So it moves like this. Caterpillar starts to move. So similarly, dislocation also moves, and you have a local strain field due to this dislocation. So you have compressive stress at the top, and you have tensile stress at the bottom. Due to these strained field present existing in the crystal, it makes easier to shear the lattice. So the presence of dislocation helps in the plastic deformation to take place, and ultimately what happens is that this dislocation shifts and it goes to the edge. So you have a bias vector here, dislocation here, and dislocation here. This is what you actually call by plastic uh, deformation or movement of dislocation, uh, which is representative of the plastic deformation. Now, looking closely, the force applied during this process, where you have a compressive stress at the top and tensile stress at the bottom, is called Peach-Coeller force. Now, this Peach-Coeller force F is equal to the external stress, including stress due to dislocations. So there are two types of stress. One is the external stress tau that is being applied, this tau, and there is already existing stress due to dislocation. So if you combine these two, you get this stress. This dot product of the Burgess vector, the cross product of the line of dislocation slide. So the line at which the dislocation is moving. Okay. So usually it is 90 degrees. So dislocation strain is acting in this direction, whereas the dislocation glide is moving in this direction perpendicular to each other. So this Peach-Coeller force on a dislocation with line direction, that is under the external stress tau, including stress due to dislocation. So there are two uh, components of the stress. Okay, so it makes the dislocation move. Now, when we say the stress, so you can see that the shear stress has been used, but in practical situations, like if you are doing UTM tensile stress in an UTM machine, or we are finding out the hardness of a material by indentations, they all undergo plastic deformations. Now, but the stress applied in both of these cases, or the external stress that gets applied, is not tensile in nature, or it's not exactly tensile. It's it's along. It's actually principles, or you can say it's normal stress, if you say so. So, like in this case, this is the stress you can see applied tensile stress in the case of UTM. It is not tensile, it is in nature. However, if you look closely, stress is tensile quantity. Right? So, by tensile quantity means that it is not isotropic in nature, it has different components. Now, if you that is why if you break it into the different components, this is the principal component or the diagonal components. They represent the normal stress like sigma x, sigma y, and sigma z. However, the shear components are these six components. So even if you are applying a normal stress, the plastic deformation occurs due to these shear components, and it is same as in the case of indentation as well. So from this cartoon, you can see that whenever you are applying tensile stress, this is the place you can see there is a cross-sectional reduction at this point. Okay, so this cross-sectional reduction is called necking, and this is actually the plastic deformation that is taking place. So due to the action of tensile stress, which is actually acting in this direction, or the shear stress, the plastic deformation is taking place, and which is reducing the cross section at the center, is known as technique, and this shape of material used in UTM is called a dog bone shape because it looks like a dog bone. Okay, so this is how a dislocation affects the plastic deformation while we are discussing yield in crystal.